Reinforcement learning starts to get real tricky with function approximation. This is where we encounter serious challenges from scaling up our theory from small toy problems to big real-world problems. Now, before I dive in, I'll mention that this is part 5 of my 6-part series on reinforcement learning. So if you haven't been watching this series, or if you don't already understand some RL, then what I'm about to say won't make much sense. You've been warned. Here goes. Okay. In everything we've discussed so far, we've assumed all possible states are listable in a table. Unfortunately, in reality, that's often not possible. If, for example, the state is an image, then our theory so far will fail us. Because step 1, create a list for all possible images. Yeah, we can't do that. So if our goal is to handle large state spaces, and if we applied our naive methods, then we'd have a ridiculous demand for memory, a ridiculous amount of computation to do, and an absolutely ridiculous amount of data needed for good estimates. You may recall in the blackjack example, which had a tiny state space, we used 10 million games. Yeah, so we have a problem. But we also have brilliant people thinking about this for decades. Their ideas start with a change of perspective. They recognized our challenge really is generalization. That is, if an agent only visits a minuscule subset of all states, how should it generalize that experience to select high reward actions over the remaining states? And if you're an ML enthusiast, you know generalization is the holy grail of machine learning. So we have a lot of ML methods at our disposal. In fact, it'll seem we can use all of supervised learning, since our goal will reduce to approximating an entire function given only noisy samples from it. But there are RL-specific challenges that restrict the methods we can use. The restricted version of supervised learning applied to RL is called function approximation, and it's the focus of this video. We start with on-policy evaluation, where our goal is to approximate the true value function, which, if you recall, is the expected return from state S under policy pi. To be clear, this is a case where the data is generated under a fixed policy pi, and, as anticipated, the state space is large. Now, to approach this animal, it's common to assume that the true value function can be approximated by a function of that state and a parameter vector w, where w has a fixed length d. To make this less abstract, let's see an example. Say S is an image. So the state space is all possible images, and is indeed very huge. Let's also say we have 2 features of S. Each feature is a function which maps from the image to a number. In our case, the first feature is just the average of all pixels, and the second feature is just the standard deviation of those pixels. And yes, this is about the dumbest vision model you'll come across. Fortunately, it's just to see the mechanics. Okay, now we'll combine these into a vector like this. Then, if we want to make a linear value function, we would just declare that our function to approximate the true function is the dot product of our features and parameters w, where w has length 2. And that's it. That's just a dumb as dirt linear model. But don't be disappointed. This could be extremely complex. The fanciest of neural nets also take this form. What's important is to recognize that selecting w means we're choosing a value function. And we'd like that value function to match the true value function. But in this case, our job is harder than it was in parts 1 through 4. That's because we're under a new constraint. That is, the number of possible true value functions is almost certainly much bigger than the number of functions we can represent by selecting w. This is because, since the state space is large, it's very likely d is much less than the number of possible states. That means, regardless of which functional form we pick, any change to w means we'll inevitably be changing our value estimates for many states. Contrast this with what we did earlier, where we would update our estimate only for an individual state S for each time S was visited. In other words, updating one state value never impacted another, but now that's no longer true. This means we won't be able to represent the true value function even with infinite data. And that brings us to the next idea. How do we select w? What we need to do is declare what makes for the best w. Now, what qualifies for best is up for debate. But for now, let's say it minimizes something we'll call the value error. We write it like this, and it's defined like this. All this is the mean squared error between our approximate value function and the true value function. And it's weighted by this. Here, mu is a distribution over states, weighing how much we care about each state. Typically, mu will be chosen as the proportion of time our policy spends at each state. Now at this point, you may say, whoa, DJ, we got an exponentially huge space and you want me to sum over it? And you snuck in the true value, which you know we don't know? I thought you were a math communicator, not a con man. And to that I say, yeah, you're right. We'll never be able to calculate this. But despite that, we'll be able to develop algorithms that approximately optimize it. And that's pretty good. And we can do that with stochastic gradient descent, which will look quite similar to the update rule we saw in earlier videos. But we'll have to assume a few more things. First, states are visited in proportion to mu. That's reasonable since we'll be updating W as we bounce around the state space according to the on-policy distribution, which is presumably what we've chosen for mu. Second, our value function is differentiable with respect to W, which is required for calculating a gradient. And third, since we don't have access to the true value, we assume we observe a suitable surrogate for it, which we'll call UT, or the target. There'll be several choices for the target, and that'll really define the algorithm. Also, quick technical note on notation. Here I'm showing a random variable, not a value, being plugged into a function, which is not something you've seen from me before. For this, just imagine sampling a value from the random variable and plugging that into the function. That's what this means. Okay, with all this, SGD gives us a simple update rule to apply to W for each visit to a state, which is this. Soak it in, it's important. Here, alpha is the step size, as we've seen before, and here is the gradient. What we're doing is, we're nudging W in a direction that maximally reduces the error from the target. So now the question is, how do we choose our target? Let's start easy. If the target is unbiased, which means the expected value of the target at state S is equal to the true value, then W will converge to a local optimum of the value error. Granted, alpha is set appropriately. Said differently, if we reran the algorithm 1,000,000 times and compared the average of each target to the corresponding true value, and those numbers were very close, then that algorithm would converge to a local optimum of the value error. And that's really nice. Remember, our value function is any differentiable function of W. So a local optimum is the best we'll get. No one out there training neural nets is finding a global optimum. An example of this is gradient Monte Carlo, where the target is just the return. To paint this algorithm for you, outside the update rule, this algorithm is virtually identical to the MC evaluation algorithm from part 3. If you recall that algorithm and understand this tweak, you know how to approximately optimize VE. Pretty cool. But MC has its drawbacks. Waiting until the end of each episode is quite a constraint, and it can make learning a lot slower. So what if we bootstrap? Meaning our target is something like this, where we're using a one step ahead value estimate as part of the target. Well, this will create some complications. First, it's biased. Think about right after you initialize W. Is the expected value of U, with your garbage estimate inside it, going to, on average, equal the true value? No. Second, and this is really weird, our target now depends on W, which is not like any typical supervised learning task. And that means the update rule is not a true gradient step. In other words, if you took this target, plugged it into the VE expression, and derived the gradient, that would be different than plugging this target into the update rule from earlier. So, that's not good. And what that means is, we don't get any guaranteed convergence to a local optimum. So now what? Well, how about just do it anyway? Who needs theorems when you got high hopes, right? And so, this is a thing. It's called semi-gradient TD. With a one-step target, the update rule looks like this. And apparently, it works well. Sometimes. Especially if we put some constraints on our value function, which we will in a moment. But importantly, this method inherits the same advantages we saw TD having over MC in part 4, like faster learning. So that's good. And now, for the sake of making stronger statements, let's constrain ourselves to a linear value function, which means our value function is just the dot product of W with x of s, where x of s is a feature vector, just like we saw earlier. In this case, our update rule becomes this. Now, for gradient MC, because this is linear, the local optimum W is the same as the global optimum W. That comes from the fact that this linearity makes our optimization convex. Next, for semi-gradient TD, specifically for the one-step case, we actually have a convergence result. That is, W will converge to something called the TD fixed point, which is different from the VE optimum. But in a sense, it's close to the VE optimum. It turns out the closeness depends on how strongly discounted the return is. For high gamma near 1, the solutions can actually be quite far apart. Now, because I don't think it yields a lot of intuition, I won't go into characterizing WTD. Suffice it to say, it's just what one-step semi-gradient converges towards. Instead, let's do an evaluation example from Sutton and Barto's book. Here's the problem. It's a 1,000-state version of the random walk task from parts 3 and 4, with a few adjustments. First, we have 1,000 states labeled from 1 to 1,000. Second, if the agent is at some state, then in the next transition, there is a 50% chance it'll land with equal probability in one of the 100 neighboring states on the left side. The other 50% is for the 100 states on the right side. The very left and right sides are terminal states, each yielding a reward of -1 and 1 respectively. All other rewards are 0. Now let's visualize the true value function, where the states are listed 1 to 1,000 along the horizontal axis. The true value function is this. This is what we'll be trying to approximate. Also, this is the true distribution of states as we bounce around. This is mu, used in the VE objective. This large spike comes from the fact that we always start at state 500. Next, let's discuss the features. We'll use 10 binary functions to indicate 10 buckets. That means we form these buckets, and our feature vector will be all 0, except there will be a 1 indicating which bucket the state is in. Next, the algorithm. We'll use n-step semi-gradient TD. The nice thing is, this includes MC if we set n high enough. In fact, let's start with MC. I'll use an alpha of this and initialize W to 0, which gives us these values. Now, if we run the algorithm over many episodes and wait, we ultimately get quite close to the VE bar optimum, which is this. So the algorithm is doing what we wanted. Now let's do TD with these choices of alpha and the number of steps. If we run it, we see that it converges a lot faster than MC, and that's the plus side of TD. But it didn't get to the right answer. It got to something off from the VE optimum, and so that's the downside. And as you could guess, setting n to something between 1 and infinity will give a solution somewhere between MC and TDs. And if you're still curious, I've included a link to the code so you can play with this yourself. But now it's time we graduate. This whole time, we've been discussing evaluation, how to value a fixed, unchanging policy. Now we discuss on-policy control with function approximation. Here we'll be looking to discover an approximately optimal policy. Fortunately, we can lean on what we've learned already to describe things fairly quickly. Okay, like every time we've studied model-free control, we have to shift our attention from state values to action values. So, using a parameterized function, we're estimating the value of taking certain actions in certain states. Next, to keep this explanation simple, let's also assume two things. First, we'll assume the action space is not large, even though the state space is. This means we can use the max operator of action values just like we have in the past. Second, we're definitely only discussing the episodic case. The continuing case actually involves an entire rethinking of discounting, and I'm going to just avoid that. Okay, with that, we can say that control is just like the algorithms we've seen in parts 3 and 4, with one exception, the update rule, which takes this form. This is just like the update rule we just saw, except we've replaced the state value with an action value. Okay, and now we can provide a control method. In semi-gradient one-step SARSA, we set UT to this one-step target. Outside of that, you can think analogously to parts 3 and 4, except instead of tables, we're dealing with parameterized functions. That's not too bad. Okay, it's time for an example. This is the mountain card problem from Sutton and Barto's book. We have a car, which I'll show as a circle at the bottom of a valley. The goal is to get here as fast as possible where the episode ends. That's encoded with all rewards being -1. Now the state space is made up of two continuous dimensions, and it's this continuousness that makes the state space large. The first dimension is the horizontal position, which we'll write as xt. The second is the velocity, which we'll write as xt with a dot above it. And the system evolves according to these equations, which are just a simplified physics in this valley. Note, our actions contribute to the velocity. The actions we can take are -1, 0, and 1, which correspond to throttling backwards, not at all, and forwards. For instance, if we hit throttle forward repeatedly, we'll start up the hill, but won't make it. In fact, the trick is to go backwards and then forwards with momentum to get over the edge. And that's what makes this hard for an RL agent. Okay, so how do we solve this? Well, let's use a linear function and determine our features. And this is where I deviate from the book just a bit. To understand my features, let's imagine the state space as a 2D plane, where the horizontal axis is the position and the vertical axis is the velocity. Next, I'll pick 9 evenly spaced points over this space. Now, if I have a particular point, like this, I'll look at its distances from the 9 points. Then I'll assign numbers to these distances such that low numbers imply far distances, all numbers are positive, and they sum to 1. This is just quantifying on a relative basis how close this point is to each of the points from the grid. And this works for any point in the space. This is how we'll define a length 9 feature vector for any point. Just as an FYI, this is called a normalized radial basis. I could show you the equations, but that wouldn't add much. Also, another FYI, I lied. I'm not using 9 points, I'm using about 1200, which just would have been a lot harder to animate. Okay, so how do we actually form our action value function? Well, it's written like this. What's happening is, we have a dot product for each action. For example, the action value of throttling backwards is the dot product of our features and a parameter vector specific to this action. And don't let this case-wise definition fool you. This could be reorganized into a linear form, so we aren't breaking with anything that was explained earlier. And now let's apply n-step sarsa. And just to convince you that this algorithm is just like what we covered in part 4, here is the code I used, which was all copied from part 4, except I only changed it in a few spots. And thank God, because it made this video a lot easier. Okay, now to get a feel for what's going on, I'll bring back the 2D state space. But this time, I'll show the max action value. That is, the value of the best action in every state. In fact, if we flip the sign, it's an estimate of how many steps are left. At the start, it's all initialized to 0, which is incorrectly optimistic. Also, I'll include the car in the valley. Next, I'll be using 4 steps, an alpha of 0.3, and an epsilon of 0. As we'll see, exploration will happen naturally, so no need to enforce it with epsilon exploration. Okay, now begins the first episode. What's happening is, as the car explores the state space, the spots visited are updated as costly, and so it avoids them in the future, which encourages it to explore further until it completes the episode. Now on future episodes, the information gained will allow it to navigate to the end more quickly. To show that, I'll show how the action values evolve over 500 episodes. And at several intervals, I'll show how the car navigates through the state space. Let me start by getting out of the way. Okay, first, we got a new scale. Earlier, the hottest color indicated a value around 3. Now, that'll be over 100. Okay, now this is how action values evolve over the first 100 episodes. The agent is learning that having no velocity at the bottom of the valley is a bad state to be in. After this, it has a rough strategy for escaping. It just involves a good deal of ramping back and forth. Obviously, more so than necessary. So, we continue learning. And now we're a bit smarter. Now, more learning. And we're smarter. Okay, more learning. Now we're really getting the hang of it. But let's learn some more. And now this is pretty much the optimal strategy. So there you have it. We were able to guide an agent to discover a nearly optimal policy inside an infinitely huge state space. And if you like this, you can check out my code where you can explore this yourself and mess with all the knobs. But be careful, RL is a delicate business. And finally, we turn to the last topic, the most daunting of challenges, off-policy methods with function approximation. And here, I'll be extremely brief. Just because this is a super hard topic that I won't be able to do justice, and the theory gives much less satisfying answers. You'll see what I mean. To emphasize what's changing, everything has been on policy in this video. That means the policy we refine to be the approximately optimal policy is the same as that which is generating the data. On the other hand, off-policy methods involve two policies, one which generates the data, and another which is refined into the nearly optimal policy. And sometimes this separation can be a hard requirement. Now, some approaches are exactly as you'd imagine. Just combine the lessons of off-policy learning from earlier with those I've covered here, and you'll get methods that people do in fact use. But stability and divergence to nonsense is a real challenge, and the book goes into serious depth diagnosing those issues. One of the most important lessons is that of the deadly triad. It says that if we combine function approximation, off-policy training, and bootstrapping into one method, then that'll likely create stability and divergence issues. And they demonstrate this by giving examples of simple MDPs with certain features where the learning algorithm diverges estimates to infinity. And unfortunately, with the deadly triad, cases like these are inevitable. So yeah, it's all a big, challenging mess. And I won't even attempt to explain it. I'd rather focus on things that work nicely, at least theoretically. So that brings me to the last topic of the series, policy gradient methods. That's the next video, so go check it out.